In this video I'm going to talk about vector operations. And so the first one I want to talk about, because I don't think I explained it very well in the previous video, is just using a matrix to transform a vector. So if we have a vector as a column vector, we'll say that it's x, y, z, and so this vector right here is three-dimensional. This is the, well, I'll just draw it right here. So we could say this is the x-axis. Then we have the y-axis, which is in the same plane. And then the z-axis, which is in the third dimension here. And so if we want to transform this, then we have to not only change the way that each of these orient in their own axis here, but in all the other axes. So if we had a vector that was something like this, we'll call it A, and we want to transform it so that it's now pointing, say, this way, so we'll call that A prime. Then we're not only changing, so when we change its x coordinate, we're not only changing its x, how much it sticks into s or x in the x direction, but also in the y and z directions. And so a matrix is what will do that for us. And so I'm going to draw the matrix, maybe a little unorthodox here. And I'll say, I'll put it like this. So I'll have an element that's a, x, x, and so that is telling us how much x is changing in the x direction. And then we'll have a, x, y. That's telling us how much x is changing in the y direction. And a, x, z. That's telling us how much x will be changing in the z direction. And then we go through all of these, so y, x, and that's telling us how much y is changing in the y direction, how much y is changing in the x direction, how much y is changing in the y direction, and how much y is changing in the z direction. And then we do the same thing for z, so z in the x direction, z in the y direction, and z in the z direction. So one thing you'll notice is in this matrix, these ones on the diagonal here are the ones telling us how much one of these elements or one of these components of our vector is changing in that in the direction of that axis. And so these on the diagonal are the scaling factors. So these are just scaling x, y, and z in their direction. So if everything else was 0 and we had numbers in this diagonal, then this A would stay oriented in the same direction, but it might grow longer. It might become shorter depending on what numbers we have in these diagonals. And so you could almost think, too, that if you have a matrix and say it's 2, 0, 0, 0, 2, 0, 0, 0, 2, that this would be equivalent. This would be equivalent. Well, I'll put our vector here. This would be equivalent to just multiplying our vector by some scalar. So this would be the same as multiplying it by a scalar. What will make it not the same as multiplying it by a scalar is if these diagonals are not the same number, or if these off diagonals are something other than 0. But anyway, the actual operation here, so you go row by column. So ax or axx times x is axx times x plus axy axy times x, and then axz times x, so plus ax or axz times x, and that will be the first part in our new column vectors. So this is equal to this new column vector here, and then we just do the same thing for the next one. So ayx times y plus ayy times y plus ayz times y, and that's how much this y is changing. So we're changing it in the x direction, in the y direction, and in the z direction. Then we do the same thing here for the z in the z direction, so plus AZY plus AZZ. And then this, when we add all these up, we will end up with some new vector. So I'll call it x prime, y prime, z prime. And that is how you do a matrix, how you operate on a vector with a matrix. So the next thing I'm going to talk about, so I already discussed in the previous video, one of the operations we can do is just a scalar multiplication. So if we have some scalar multiplied by our vector, so that would be c times, and this time we'll call it ax, ay, az, then this will just be cax, cay, caz. And so that is just a scalar multiplication. You just multiply each of these components by the scalar. And one thing I didn't mention, though, is that scalars are distributive. So if we have a plus, that should be b, that this is just equal to c a plus c b. But then to get into maybe a little bit more of the juicy stuff here, that we can talk about what's called the dot product. And so that is, if we have, say, this is our vector A, and this is our vector B, this will be the same as saying that this is A, and I have the absolute value written here. So that's our vector A multiplied by our vector B multiplied by cosine of theta, where theta is the angle between them. And what this is doing geometrically is if we sort of shine a light on A, so that it's perpendicular with B here, we are looking at how much of excuse me, we're looking at how much of A is sort of casting a shadow over B. And this is sometimes also called the scalar product, because what you get from this is a scalar. You do not get another vector from this. You just get a scalar from it. And this is the same thing as, so we could say that this here is the same thing as if we had A dot B, and that will equal the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. And this could keep going depending on what the dimensionality of your vector is. I have 2 here, but I wrote this in 3. So if it was just a 2-dimensional vector, then you would, you would remove this from it. Yeah, sorry. You would remove this from it. But if it was in more dimensions, then you would just keep adding up to, however many dimensions it is, where n is the number of dimensions that it is. And so, like I said, this gives a scalar, so all of this will equal some scalar, which is just a number. But then we can also do what's called the cross product, or sometimes called the vector product. And that is because you are multiplying 2 vectors and getting another vector. And so that would look something like this. So if you have your vector A cross your vector B, that will equal some vector C. And so essentially what this is doing is, if you have your vector A, say like this, so A, and then you have your vector B, and we'll say that this is in the same plane as A, then what you're doing is you're sort of making a parallelogram out of this, and the area of this parallelogram is going to be translated into the length of a vector. So if this area was larger, the vector would be longer. If it was smaller, the vector would be shorter. But that gives us a vector that is perpendicular to both of these other vectors, so vector C. And like I said, the length of this, so the length of this is equal to the area of this parallelogram here. And so if your parallelogram is not if it's not a perfect square, so then you have to, then it will be the same as, as if we have the absolute value of A multiplied by the absolute value of B multiplied by sine of theta. So if this is our theta, and that is because if we have a parallelogram that's not a square, so think of this as being flat here, then a square we could think of as being sort of like this, and this side here might be our B, and this side here would be our A. But the volume, or the area, is not going to be the same as that, and so we have to use theta here, because that's opposite over hypotenuse. So it's giving us the length of B here, since B is the opposite here. That is the opposite of our hypotenuse here. And so that is giving us the new length for B. But then we're just multiplying it by A, the same you would do if it was a rectangle. And that gives us the area of it. And so that is what C, the new vector here, will be equal to. And so the way that you can do this, you might have seen something that looks like this. So we have A cross B, and this is equal to, so we'll have our basis vectors, so E1, E2, E3, and then we'll have the components for our two vectors here, so AX, AY, AZ, then BX, BY, BZ, and then I'll put bars around this. And then what you do is you sort of go down along these basis vectors here, And when you get to, when you're at E1, then you take a y, so a y, multiply that by bz, so a y bz, and then you subtract by times az, so by times az, and we'll put that in parentheses, multiply it by E1, our basis, and then you go on to the next one. So that was E1. So plus, and then we'll take A3, or AZ rather, AZ, and multiply that by B1 minus, and then AX. I keep using these numbers because that's how I have it written in my notes here, but this should be BX rather. I don't know why I changed it when I wrote this, but so BX and then minus AX, so AX times BZ, and then we multiply that by our basis here, and then we continue down. So now we move on to E3, and so that will be AX times BY minus AY times BX. And so you can see that you are just using the components that are not underneath the basis from which you are at. So we were at E3 and we used AX and BY and AY and BX while we were under E3 here. So E3, and that is how you actually calculate the cross product using the components of our vector here. And so one other thing to remember too is when you're taking the cross product, so I'll look back up here. So this is using the right hand rule, where you can think if you have your index finger pointed in the direction of A, and then you sort of twist your middle finger in so that it's pointing in the direction of B, then C is the direction of your thumb. And if you switch the order of this, if you instead did B across A, then this C would actually be pointed in the other direction. And so that would be minus C. So this up here would actually be pointing down in that direction there. And so you might then be asking yourself, so if we have this scalar product, the dot product, and this vector product, which is the cross product, can we combine these things together? And the answer is yes. And so there is something called the triple scalar product, which you first take the cross product, and then then this would give you some vector. It would give you that third vector, and then you take the dot product of a fourth vector with this vector here, and what that gives you is the volume of this thing, which is called a parallelepiped, which is a fun word to say. So instead of a parallelogram, it's a parallelepiped. And so essentially you're taking the cross product of A and B, which gives you this vector here, and then you are taking the dot product of this vector here with this vector here, C. And so that is just the same operation that we did with the scalar product above. And you can also do it with a triple vector product. So you first take a vector product, which will give you some other vector here. I'll just call it D, so that would be this one here. And then you just take the cross product of D with the other vector here. And so you're essentially just doing the cross product twice. So we have our B and C here, and this BXC, this B cross C is the area of this parallelogram here. And then we have another parallelogram here made with A, with our other vector here, and we're just taking this cross product of A with this with D, which was the cross product of B and C, which is just another area, and then we make this vector here, which with the length of which tells us the area of this other parallelogram here. And this will be in the same plane as B and C, because this was perpendicular to it, and so perpendicular to this will be in the same plane as B and C. And so that is how you do the triple or vector cross product. Yeah, so that is what I wanted to talk about as far as vector operations. I hope this was somewhat enlightening for you, and I will see you in another video.